Hello, and welcome back to Shiksha. So today we're going to review that double unit on connecting graphs and equations of exponential functions and solving problems that involve exponential functions. So in the first half of this unit, we learned how to simplify and evaluate numerical expressions that involve exponents. And then we also made a lot of really deep connections between the numbers, the graphs, and the algebraic representations of those exponential functions. And we did that by evaluating. Throughout this unit, we determined through an investigation what is the value of a power that has a rational number as its exponent. We also were able to evaluate exponents or powers that have integer and rational exponents. We figured out how to graph an exponential relation both with technology and without technology. And we also defined exactly what that was. Hopefully by now you've also determined through an investigation all the key properties of exponential functions like domain, range, intercepts, increasing and decreasing intervals, and asymptotes. After that, we determined, actually much before that, we determined the exponent rules for multiplying and dividing powers, as well as the power of a power rule. And finally, as part of that first part of the unit, we were able to tell the difference between an exponential function, a linear function, and a quadratic function in all sorts of different contexts. From then we move to the second half of the unit, which is about solving problems that involve exponential functions. We collected some data that can be modeled as an exponential function. We found out other exponential functions that come up from the real world and how does the domain and range of those interact with its ability as a function. And finally, we solved problems using graphs or using equations of exponential functions that came out of the real world situations. So first we learned the exponent laws. We learned that when you're multiplying two powers that have the same base, you can just add their exponents. We learned the quotient law, which says when you're dividing two powers with the same base, you can subtract their exponents. And the power of a power law, which says when you have a power of a power, you can multiply the exponents. We also very briefly touched on the power of a product of exponents, which means you just sort of use almost like the distributive property to apply the exponent to any exponents that are on the inside of the base. And also we learned what the value of a zero exponent was, and that's equal exactly to 1. A power that has a negative exponent and an integer base, we also learned how to deal with that. We just recognized that, okay, if we imagine that this is over 1, we could just take the entire power and move it into the denominator, just like that. And that would turn the exponent from negative to positive, or from the denominator to the numerator. And as part of this, we recognize that our final answer should only ever have positive exponents. For example, one of the places we use integer exponents is with scientific notation. That allows us to take a really big and a really small quantity and express them in the same sort of situation using the same unit even. And then we learned about rational exponents, and we learned that whenever we're simplifying, our final answer should only have positive whole numbers. And while a negative exponent moves the entire power to the denominator, a number that's raised to a rational exponent is equal to a radical, like a square root. So if it's to the exponent 1 over n, that indicates the nth root. However, if the numerator is not 1, well, you can still change that to the nth root, except if the numerator is m, that would be the exponent on the outside or on the inside. We learned that f of x equals a times b to the x is the actual definition of an equation of an exponential function. But there are some restrictions here. B has to be greater than 0, can't be 1, and a can't be 0. All of these things would make the graph look very, very different from all of the other values. If this b value is a small number, so between 0 and 1, the function will decay, which means it decreases over as x increases. Anything between 0 and 1. But if it's greater than 1, that means the function is actually growing. So it's actually increasing over time. All exponential functions have an asymptote at y equals 0. That's an imaginary line that the function gets closer and closer to, but never actually touches, and a y-intercept of 0 and a, whatever the a value is here. The graph of an exponential function looks very similar to one another. It's really flat on one side and then it rises very sharply on the other side. The domain is any real number, and the range is any number as long as it's greater than 0, not equal to, because that is the asymptote. Okay? And that implies that there is no x-intercept, even though there is a y-intercept. To tell an exponential function apart from a linear or quadratic, you can find that if the table of values has common first differences, it's linear, second differences, it's quadratic. But for exponential functions, we look for the common first ratios. And their equations look like this: mx plus b for linear, ax squared plus bx plus c for quadratic, and a times b to the power of x for exponential. And finally, they're graphs. The linear graph looks like straight lines. That's where the word line comes from. Quadratic, that comes from the word quadratum, from the x squared term, and that always creates a very special shape called a parabola. And finally, the exponential function, like I mentioned, has a really flat side and then a really steep side. Now we started solving problems that involve exponential data. So we started off by collecting some, and stuff like repeatedly doing a probability experiment or a situation that involves inflation or population growth. All of those create exponential relationships. And you can generate your own data using that experiment, or you can even find secondary sources that you trust to download data. Once you have the data, if the graph appears to be exponential, so if it appears to be increasing slowly and then quickly and faster, you can find the equation of it by using a technique called regression, which involves putting your table of values into a graphing software, and then for example, the graphic software I use is Desmos, then putting in an equation that looks like this, and that tells you the A and the B value that creates a curve. Notice this is the blue curve that very closely matches all of these orange dots. And the values that will create this curve are A would be 32.1626 and B would be 0.501699. Exactly the way you see here. So the equation of this curve is A times B to the power of X. In the real world, exponential relationships are used for increasing or decreasing by a percentage amount repeatedly. And so we're going to modify our exponential function very slightly. We're going to change the b value to either 1 plus a number or 1 minus. And this is super, super useful, especially for calculating things like compounding interest. And we would need to limit the domain and range of our exponential function in the same way that we might need to consider the domain and range of a quadratic depending on the situation. And finally, when we actually want to start solving for the independent variable, if you're given a value for the dependent variable, for example, let's just say that number is k, whatever number k is, you can plot that on your graph and draw a horizontal line out from that, and then look for where does my horizontal line intersect my actual graph. Wherever it does, for example, there's one right here, just create a vertical line going straight down to the horizontal axis, and that tells you the value of x that will actually give you that value for the dependent variable y. And there can even be more, 1 or 2 or 3 or even as many as you can think of for certain functions. For exponential functions, though, there will usually be just one. Now, if you're using graphing technology, you can actually graph the line y equals whatever this number is, and it'll graph it for you, and then you can just click or tap on the points of intersection to see its coordinates.